All right, the next section that we have is arc length and speed, 13.3, right here. So speed, we already talked about this. If you have a parameterization, so if you have some path being traced here by, let's say, r of t, so here's some orientation arrows on here. Then, so I'm just going to say r of t, that's the trace. Then at some point, let's say like right here, there would be some tangent vector, your line of sight. So this is the r prime of t at that point. So r prime, so let's just say this, r is position, and just like in Calc 1, the first derivative of position is velocity. So velocity is a vector quantity. Speed, on the other hand, is a vector quantity. So this is the magnitude of the derivative, is speed. So if you know what your speed is at all times, and you want to know how far you have traveled, then that is exactly what arc length is. So for instance, on this path here, if we go ahead and limit this, let's say this corresponds to some initial value t equals a, and instead of making this a arrow, let's just make this a dot. We could stop at some final time t equals b. So then the actual traveled distance, so the length of this curve, would be found by integrating your speed over the duration of your travel. Start time to finish time. Also in this section is something called an arc length parameterization. Arc length parameterizations sometimes show up on the final, but I will say they are not a very big aspect of any exam, especially not the final. So if you are asked to calculate it, this is a step process. So essentially, what you do, we'll do an example of this. So given, let's say find an arc length parameterization of r of t equals, let's do cosine three t sine of 3t, and let's make this let's just make this 4t. Let's find an arc length parameterization of that. Okay, so an arc length parameterization is any parameterization let's just define this up here. So an arc length parameterization, any parameterization that has constant speed equal to 1. So as long as the speed is always 1, in other words, no matter what your path is tracing, the speed is always 1. You're always walking at the same speed of 1 on your curve. Doesn't matter what's being traced, just that the speed is constant and equal to 1. So, to do this, we are first going to set up this. This is the arc length integral. So we're going to find the arc length. So the arc length of r from zero to some arbitrary final time t is the following. This would be s equals the integral from 0 to t. Now, since we're using a t up here, we don't want to use t in our integrand because then we'd have two different, we'd have t and t, but this t down here is not the same as this t up here. So because they're not actually the same, we'll go ahead and just replace this with some other variable. It doesn't matter because when you do an integral, whatever this variable is, it goes away. And I just noticed this should not be bolded. This should just be regular u. So let's do from 0 to t. So here in this case, we're just using a equals 0. So the magnitude of the derivative. So the derivative, we'd have minus 3 sine t, minus 3 sine of 3t, comma, 3 cosine 3t, comma, 4. So this will end up being 9 sine squared 3t plus 9 cosine squared 3t plus 4 squared, which is 16. We've got the Pythagorean identity here. Oop, and we need a d, excuse me, I should have used u's. I always do that. U, du. There we go. So the inside of this turns into just 9, and then 9 plus 16 is 25. So the square root of that is 5. So this is 5 du. So the answer is s equals 5t. So then we can solve this for t to get s over 5. And then we can replace the t's, in our original parameterization, here, here, and here, with this new expression. So this creates a new parameterization. Let's say it's r sub 1. We'll just give it a different name. We'll use the subscript of 1 to denote that the speed is 1 unit per time. So this would be r1 of s. And this would be cosine 3s over 5, comma, sine of 3s over 5, comma, 4s over 5. And that is an arc length parameterization.